Hi everyone, we'll wait for another minute, okay? And if you guys don't hear me, please let me know, okay? Because sometimes there was a problems with the audio. Okay, I'm getting feedback, that's everything. Okay, what's going on with Alexis? Okay, so apparently some of you, at least Alexis, is having an issue connecting, and probably others too. But at this point, we have not many actually. I don't know what's going on. Anyway, this is the last chapter for this class, so we're going to cover the basically the moons of the outer planets mainly. We'll also talk about the one of the dwarf planets, at least it used to be a planet, namely Pluto, and also its moon. Depends on who you ask, either Charon or CHARON. And then we also talk about the rings, namely the rings of the outer planets. We'll focus more on Saturn's rings because they are actually more exaggerated, if you wish. I mean, they are actually landmark when it comes to the solar system, is the planet Saturn. But all the outer planets have moons. Have rings. So basically, we'll talk about the ring systems and see exactly when and where does the ring system form and the reason how it's forming and so on and so forth. So that's basically what this chapter is all about. I said before that maybe, and I don't think that we are going to cover stuff beyond this, namely the asteroid belt and also maybe even the Kuiper belt and also potentially even the Oort cloud. That is not probably going to be covered in this chapter because we have quite a few more things to do for this class. Namely, we have 2 more assignments that we need to deliver by the end of next week. And also we have exams, basically exam 2. And so there are at least 3 more assignments that are needed for this class, in addition to another quiz. So that's 4 big stuff that is required, and I think we don't have enough time, given the fact that in about 2 weeks from now, the school is going to be out. So I don't think that we're going to go to chapter 13. So that's basically as far as the overall picture of where we stand. So this is it. This is the last chapter. Chapter 12 is as planned before, because apparently this is how this course was also taught. And when I planned it, I followed the plans from before. So I was hoping to squeeze in something else, but we cannot. Okay. So I'm glad Andrea was here, and she is still here, because there will be a few assignments, so maybe we can also take advantage of the fact that she's here, and you guys can also use her as a resource to make sure that she's, that you do all of your assignments in time and so on and so forth. So let's share with you guys where we are. I already sent you today, and because we went through transition, actually I didn't do this before, so I kind of apologize for it, but it's better late than never, which is I sent you already the notes for this chapter, and they should be already on Canvas. So I'm hoping that for those who do not attend the live sessions, they will have access to it later on, so that they can follow and take notes. And you too, actually, too, you follow and take notes and basically add whatever you think is important, and hopefully that will help you also prepare for your exams. So basically, this is again about the rings, the moons, and Pluto, because Pluto has a story with it that apparently that we need to cover, because at some point it was considered to be a planet, then it was demoted to a dwarf planet, and we'll talk about why, the reason that is. And it's actually an interesting system as is, because you will see that it's not just a dwarf planet like any other dwarf planet, although others are actually interesting too, like Eris, for example. But it has actually moons. It has 5 moons. We'll talk today about one of its moons, namely the biggest moon that it has, and actually, relatively speaking, it has a big moon. And it's only, it's actually the first before even Earth, because Earth also has a big moon too. Okay, and when I say big in this case, it's compared to its actual size. I don't mean that it's the biggest moon. The biggest moon, of course, all of the moons, they are actually in the Jupiter, and one of them actually is in Saturn. So those are the moons, basically, as we know them. So again, these are the objectives. We're going to talk about the ring and moon systems, basically big introduction. And let me get the other thing going also. I'll pull in that too. Anyway, oh man, that's loud. Okay, I'll do it later on. That is very loud. Anyway, basically, I don't know if you guys heard that background music or not. Did you guys hear it or not? Because it's part of the other animation that I probably should have canceled it. Okay, keep that in here. Okay, so it's good. That's fine. Okay, so basically, so we're going to talk about the overall picture. Basically, we're going to talk about objects outside of the frost line, basically all of the objects in the outer solar system, and they're all basically the smaller objects. Turns out that they're actually extremely important and they have a lot of things that they tell us. They have a lot of features that we need to know about. And as a matter of fact, as you will discover more and more about these moons, it's probably, when we're looking at exoplanets and things like outside of the solar system, it may very well be that the moons is actually where we need to be looking at. It means that it's probably that's where interesting things are going to be happening. In here, you have a depiction of four of the moons of Jupiter. This is the so-called Galilean system. In 1610, Galileo, after he modified the telescope, a toy that people used to play with, and basically directed it toward, among other things, to Jupiter, he saw, at least the first night, he saw 3 moons. He saw this one. This is actually Callisto. He saw Ganymede, and then he saw Europa, 3 moons. The day after, the night after, he saw the 4th one. He saw Io. And that's why they're called actually the Galilean systems, or the Galilean moons, because of the fact that they were discovered in 1610 by Galileo. And that was one of the first indications that that basically put a dent in the so-called heliocentric, in the geocentric model, where the Earth is supposed to be the center of everything. That, hey, look, here is Jupiter, an object that is in the sky outside of the Earth, and that one, it has 4 objects revolving around it. Well, we know today, actually, there are more moons around Jupiter than just these 4. This is just the big moons. There are about 60 some odd number, 69 or something like that. I think there are more than that. There are 70 something. And it seems like every year we discover more moons, and they're kind of small. Sometimes they're very tiny. And that's basically what Jupiter is. In case of Saturn, turns out Saturn also has almost as many moons as Jupiter does. And Saturn has 60 some odd moons, I think 62 moons. The biggest of which is Triton. Triton is the big moon. So one of the objectives of this class is, hopefully it will introduce you to, at least this lecture, is to introduce you to the moons of that are outside of the solar system, and you'll be familiar a little bit with their names so that you know what they are, and know also their sizes. These things are big. I mean, compared to, for example, planets, these things are big. Let me get this thing in here. They're almost the same size as Mercury, and Mercury is a planet. I'm going to stop sharing that screen, and I'm going to share with you another screen. And the other screen is the universe inbox. Okay, so these are, let me put them in order a little bit. Okay, So these are in size some of the moons. And I'm going to remove this one a little bit because I don't have. Let me see if I can do this quickly without having to. What is the settings in here? I'll forget it right now, okay? Oh man, I'm trying to get rid of this sound in here and I don't seem to. Audio, I'm sorry. There's audio. Okay, good. Okay, so these are the moons that we're going to be looking at. This is basically Mars. Mars is big, of course. It's a planet. It's compared to, for example, Mercury. This is Mercury. I'm sorry. This is Mercury, and this is now Ganymede. This is the biggest moon in the solar system, bigger than any other moon, including our own moon. And look at the size in here. It's not much different, really, than Mercury, which is a planet. Then comes Triton, which is a moon in Saturn. Then after that comes Callisto, which is another moon of Jupiter, actually. And after Callisto comes Io. Io is a big moon. I mean, it's relatively speaking, it's a small moon compared to the others, but it's a big moon. It's actually bigger than the Earth's moon. This is the Earth's moon. So it's big. And then you have, after that comes Europa, okay? So this is Europa. So those are the moons in here. This is our moon. So these are big objects. And then after that comes Rhea. And I think I'm missing one of the moons of Uranus in here. And this is CHARON, actually, or Sharon, depending on who you talk to. And there are smaller and smaller moons, including Mimas, okay, and smaller ones. So the point being in here is hopefully you will have at least 5 moons that you're going to be remembering by the end of today's lecture, and relatively their sizes, relatively speaking, their sizes. The 4 moons of Jupiter, the moon of Saturn, Saturn, and then at least the moon of Pluto. Those are 6 in addition to the Earth's moon. So those are the things that we need to be more familiar with, more or less, because they're part of the things that we will be talking about in this lecture. But of course, the more we know, Enceladus, for example, one of the moons of Saturn, which is an interesting object in there, not too much different than Europa. And Europa has so many features that people are talking about, that potentially it has life and it's subsurface. In addition to the fact that Titan itself might have a life, carbon-based life that did not evolve the way that life evolved, potentially like it did on Earth. So there are things in here in terms of the biology that is probably different than ours, not too close to ours, that is potentially out there. I mean, when it comes to Europa, for example, or even Enceladus, there is potentially that the life is, we know it's on Earth, but it's probably an ocean-based life, maybe microbial life or something else. So those are the things, those are what makes actually this moons more interesting, is the fact that they can harbor life either as we know it or actually in a different format than what we do. So that's what prompts people to think that, hey, when we look at the exoplanets, maybe instead of focusing on the planets themselves, and maybe even on rogue planets that don't belong to any kind of a star, they're basically ejected from their own stellar systems, and those planets may have moons around them that probably can have life on them. The biggest question at this point is, and we'll try to answer that today, is how do these moons get their energy? I mean, you will see, for example, that Io is probably the most volcanic object in the solar system. You can clearly see from this image in here, actually, it's not much different than the Earth's moon. Earth's moon is dead, geologically speaking. It's not doing anything. There is no geology on its surface. Whereas this guy in here has volcanoes in the hundreds, okay, that we could count, that we could see. So this is still a super active, the most active volcanic object in the solar system, more than any planet or anything else. So that's really some of the things that we'll try to answer also today in terms of where does it get this energy from? In terms of the Earth, for example, and Venus, we can think about the core and radioactive materials and making the energy in their core, and that's what probably heats up their core and makes magnetism. But when we study this object, we have to come up with a different explanation to it. So that's basically, in a nutshell, the introduction that I wanted to get first before we delve into the topic itself. And so this is in a nutshell, basically what we want to achieve from this one. So the first thing first, okay? So we're going to talk about the 4 moons. So that's basically let me get into this picture again in here. This is again a similar comparison, but it gives me actually more moons lined up by their planets. And we throw in here in the mix 2 things. First of all, the Earth's moon, which we're not going to be talking about. We dedicated a long time, a chapter on it. And actually the Earth itself also in the picture to see how big these objects are. So that's and they're lined up by their planets. For example, in here, Jupiter, the 4 moons I just mentioned, and you have Callisto, and I think they're aligned in here in terms of how far they are from their host planet. The closest one is Io, and Io, we say it's very close, and you will see it's not really that close compared to how the moon is closer to the sun, to the Earth, I'm sorry. And, but it's close enough. It's the closest among all of the moons, followed by Europa, followed by Ganymede, the biggest moon in the solar system, and Callisto, which is a dead world, basically. It's a very, very old object compared to the other ones. And you will see the distance plays a role in here when it comes to their ages, the surface, basically, age. And Saturn's moons, the biggest one, of course, is Triton. There is Enceladus in here. That's an interesting object. Dione, Rhea also is an important one. So those are some of the important, the moons of Saturn that we will be talking about. And then Uranus, the biggest one probably in here, Oberon, but the one that is probably important is Titania. And you have to make a distinction between Titan and Titania. They're not the same thing. And they're actually from Uranus. And Uranus also has a lot of moons, has almost 30 moons. So it's also has a lot of moons. And then when we move further away, we have Triton. Triton is the moon of Neptune, and it's a big moon. One of the odd things about Triton is it orbits basically, it revolves backward. It moves in a retrograde motion. So that's one of the things that is interesting about Triton. And it's a big moon, so it's not a small moon at all. So this is for Neptune, and it has also some quite few moons, also about more than a dozen moons. That's at least the ones that we were able to find. Now, Pluto is a dwarf planet, and it has actually 5 moons. We expected to find more when we sent New Horizons there to look for moons, and we found only 5 moons. Depending on who you ask, there is some people, they call it CHARON, because that's how actually the person who discovered it called it. And actually in honor of his wife, but and he found the correlation, and there is a story there. He found the correlation between Charon, the character from the mythology, so, and the spelling is similar. So that's basically why he used that name. So that's why people, they use different ways of saying it. And you have Eris also has a moon. That's another dwarf planet out there that we discovered. That's why actually Pluto was demoted, when we discovered a bunch of them actually in the same region where Pluto is. So those are some of the moons that we'll be talking about today. The focus is, again, is going to be on these 4 moons, probably this one also, Titan. Maybe we'll mention in the passage Enceladus, and also Miranda actually is one of the moons that actually also a lot of features in it, and Uranus. And then we'll talk about Triton, and then we'll talk about the Pluto system. So that's basically in a nutshell. And then we're going to talk about the rings, of course. That's another thing that we'll be talking about in this thing. And we will see that there is actually a pattern, that there are rules for the rings and how they form around planets. Good? That's a good plan? Okay. So again, the Galilean moons, they're basically discovered in 1610 by Galileo. And that's why they're called the Galilean moons, because of that. And they rank in from further to closer, Callisto, then Ganymede, then Europa, then finally Io. And we will see that this classification, or at least the distance, plays a role in this one. But before we get started, let me give some numbers in here, because that's important that we have to remember that. In terms of size, of course, I've been saying that this is Ganymede. Ganymede is not too far compared to Mercury in terms of size. And also followed by actually Titan. That's the moon from Saturn in terms of diameter. This is diameter. This is how big it is, basically, from end to end. Okay, half of that is the radius. So if you're going to be doing densities and you have problems dealing with densities, don't forget to divide this number by 2, because this is the diameter, which is twice the radius. Okay. Then after that comes Callisto, which is another moon of Jupiter. And after Callisto comes Io, which is another moon of Jupiter. And after that comes the Earth's moon. The Earth's moon is big moon. I mean, Venus does not have moons at all. Mercury doesn't have moons at all. And Mars has a couple of basically asteroids, very, very tiny ones that basically, if you can consider them moons, that's what it has. So in terms of planets, inner planets, the Earth is an odd object. It has a moon, and it's comparable in size to the big moons of the outer planets too. So that's why those theories that say that they basically that's the formation of the moon on the Earth was probably due to a collision may not be far-fetched, because in a sense that's probably how it's happened. Otherwise, we would have seen moons for all of the other planets. When we do models, for example, and have something called the solar system makers, they're hardly going to make an inner planet with the moon because of this fact. So that's one of the odd things about the Earth moon. Then after that comes Europa. Europa is a big moon too. That's the size of the moons. So those are the 6 objects that you guys need to have an idea of their names and their locations and things like that. The masses are no different. They follow suit. Actually, the same thing. There is 2 times the mass of the moon. So all of these units are versus the mass of the moon. How many moons is this objects are? Based on the diameter, which is, you can deduce from it the radius. Based on the mass, you can find the mass, relatively speaking, to this. I mean, the density, relatively speaking, to the density of the moon. All you have to do is take this number, for example, 2, divided by half of this number cubed, but you have to express it in terms of the moon's radius. So you have to take this one over that one, find the ratio, and cube that number, divide this by that ratio, cubed, of course, and you will find this number, the densities. Note the following. It's very, very important to note this thing when it comes to density. It seems like Europa, Io, and the Earth's moon are not too different in terms of composition. They look similar in terms of how much rock and basically structure. And so why is that? Why, for example, the other 2 moons, for example, of Ganymede and that of also Triton, they have densities that are much, much lower. They seem to be composed probably half water, half rock, versus the others that are probably dominantly rock. So that's one of the things that we need to answer to today. And it's probably because, again, during their early formation, the Jupiter, because they were too close from it, was emitting a lot of radiation, and maybe that's how the water evaporated on this. At least a lot of their water evaporated, because Europa still has a lot of it, but it still has a core of it. So to a core that's probably a rockier core. That's why it has this much density in it too. So what happened here? Let me go back to the slide. So that's why its density is kind of high. Relatively speaking, the other 3 objects, they have almost the same density, which is of 2. But their sizes are different. So that's something that is interesting in here. Now, another factor that we never talked about so far in this class, and that is the coefficient of reflection. If you shine light on a surface, here, okay, how much light is reflected back versus how much it's received? Well, believe it or not, my hand would have very low reflection. I mean, most of the light is actually, a lot of the light is absorbed on my skin. And that's something that is actually true to a lot of materials. They absorb light and reflect very little. The moon looks bright to us because it reflects a lot of light, but as relatively speaking, it reflects only about, 12% of what it receives. And as you move along in here, you will see that the coefficient of reflection in here, for example, for Triton is low too. What's going on in here? There must be something with its surface. There must be something with, probably it's the cloud structure that it has. And indeed, that's what's probably is going on. And there is a lot of chemistry going on into its atmosphere. And we will see that that gives it probably potentially a lot of chemistry there. And it has a lot of carbon-based, basically, activities in there. So that's one thing. The other moon also is Callisto, which is far away, that also similar to our own moon, basically. It observes, it has a rocky surface or whatever the surface is, it reflects very little. If we go back to that game and we actually do the actual, how it looks like, the luminosity, you will see that they look very dark, basically, up close. Because again, they have very low coefficient of reflection. Now, this guys in here, they reflect more. First of all, IO, because of the fact that it's geologically active and it has a lot of materials that's on its surface, so it reflects more. Europa has an icy structure on its surface. That's the ice, basically reflects more. When you look at clouds, when you look at the surface of any planet and you see a lot of white on it, that's an indication that there is clouds on its surface, probably. That's basically what these coefficients are high. Ganymede is relatively medium size. So this is something that we throw in today in here, so to have an idea of how these things are, okay? So, Callisto. Callisto is about 2 million kilometers from Jupiter. It's far, okay? To give you an idea, the Earth's moon is about almost 400,000 kilometers from the Earth. So this one is about 5 times, probably more, 5.5 times further from its planet than its host planet than the Earth's moon is. So just one thing. Then the other number also, and that is actually Kepler's law, it takes 17 days to go once around its axis, basically. I'm sorry, it goes around the, what am I talking about? Around Jupiter. So its period now is at 17 days. And actually, it's also revolution is also 17 days. So it's tightly locked, basically. It's just like the moon. The moon for Earth does 30 days, almost 30 days around the Earth once, and also does the same thing. The day on the moon is about 30 days. Same thing in here. The day on Callisto is 17 of our own days, and also the Callisto month, if you want to call it the Callisto month, as it goes around around its own planet, it's also 17 days. So that's something that we need to do. And that's some of the facts about this one. Again, the biggest thing in here is the furthest from the, in terms of the big moons, from Jupiter than any of the big moons of the Galilean systems that are there. Now, what is this thing called approximately zero? When Galileo, which is the orbiter that was sent in there, collected the magnetic readings around the moon, it found basically hardly any magnetism whatsoever. So that means it has basically a almost no core, no molten core like the others. So it's just basically like the moon in terms of its activities. No magnetism, no geology. It's really a dead wood, as you can clearly see from this picture. It has a lot of impacts, craters in here. That's indication that its surface is old. So basically, whatever happened in the past, and it never changes. Again, the distance plays a role. So now, if we go to Ganymede, which is the biggest moon in the solar system, bigger than Callisto, and it's a little bit closer. It's actually halfway. It's 1 million kilometers from the Jupiter. And of course, again, Kepler's law still works in here. The closer you are, the faster you're going to revolve. And this one also is tightly locked. Does 7 days. Its period of revolution, it's 7 days. It goes once around the Jupiter. And this one has magnetism. This one, if you can even see the surface in here, it has some impact, some craters in here, but it also has some geology. Now we're getting closer. It seems like the fact that you're closer to Jupiter, you receive probably more energy in the form of tidal friction, basically, because especially if you're moving around in here, you're being pulled and torn apart. So that builds energy inside of it. And it seems like there is a core, maybe there is an ocean also underneath of it, that's probably made out of salty water, and salty water is conductive, which gives it magnetism, just like, for example, the case of the Earth that has iron and nickel in its surface. Now, the density of this guy is about 2 grams per cubic centimeters, which is a candidate for being almost half water, basically ice, and the other half is rock. So this one has the structure ideal for that. So that's the one thing about this morning here. Now we're getting closer now. When we go closer to Jupiter, by the time, please remind me to take attendance in about half an hour, okay? So that we have everybody who is here at least to be accounted for. Okay, we're getting closer. Again, now we are 670,000 away from Jupiter. This is close now. This is compared to the other two. This is 2/3 of the way as far from Jupiter as is Ganymede. So this one is closer, okay? And so it's closer, so it must take less time to go around the planet. Again, Kepler's law. And it's tidally locked, and also it does 3.5 days around the planet, around Jupiter. So it's super fast. It moves very fast because it's close enough to it. Remember, the reason why they move so fast, I mean, the Earth is 300, I mean, if you take the Earth's moon, it's 300,000. So you think, oh, 300,000 is less than 670,000. So in here, shouldn't then the moon go a lot faster than the 30 days? No, the reason why that is the case is because the Earth's mass is less than that of Jupiter mass by a factor of more than 300 times. That's why you don't need to go that fast to stay in orbit. On here near Jupiter, you need to go super fast in order to stay in orbit. Otherwise, if you go any slower, you're going to actually smash onto the planet. So that's why they go super fast in here. Only 3.5 days. So that's for the case of Europa. Now, Europa's surface shows a lot of activity. This has no basically cratering whatsoever. So whatever impacts happens, the surface renews itself all the time. As a matter of fact, these ridges in here, they seem to be openings in the cracks, basically, in the surface of Europa itself, and they're laying on top of one another. Look at it. It's like the highway, basically, like Interstate 10 when it meets 210, when it meets the 15 everywhere in here. So it looks like there are highways in here everywhere, but one of them are more recent than the other ones. The ones on the top, of course, are more recent and the ones that are in the older ones. So you can actually just basically by looking at these ridges in here that are forming, and the cracks that are forming in the surface, basically tell the activity that this is a super active planet. So it must have some sort of an energy in the bottom and inside of its core, and that energy must be coming somehow because of the fact that it's somehow being basically needed, like here, like when you do the dough, by its neighbors, basically. The biggest one, of course, is Jupiter, but don't forget that it has also a couple of big neighbors, especially Ganymede. So Ganymede is pulling on it one time, IO on another time, and IO is bigger than it, bigger than Europa, by the way. So, and also Jupiter. So imagine with me for a second that if I have them all lined up in such a way, this is, for example, let me try to do it in such a way that we can see. Okay, this is, for example, where Europa is today. And then you have next to it, of course, IO. Let's put IO in here. And then you have Jupiter, and now you have Ganymede on the other side. They're all pulling it one way. The next time it's going to move, and it moves fast, okay? This thing happens fast. So the next time it moves, probably, it's going to have them lined up so that it's in here. So the pull now is on the other side. So it's basically being pulled here and there. And that is basically how you find its energy. So the material that is inside that makes the planet itself is being squeezed one time this way, another time the other way, and it's squeezed and deformed all the time. This motion itself, which is fast, this thing goes 3.5 days once around Jupiter, versus the other one that takes what, 7 days. So by the time it goes once, twice, it's going to find where it found last time Ganymede, because their periods actually on some fixed ratios. As a matter of fact, there is a time when all three of them will be lined up this way and all three of them will be lined up this way. And this is the tidal locking actually that is happening in here is periodic, and this is periodicity plays a major role in terms of basically changing all kinds of dynamics inside in there. So this resonance, which is actually called the resonance, plays a major role into the source of the energy in the planet and the moon itself. This is not as dramatic as the case of IO. IO actually is closer to about slightly further than the moon is from the Earth than it is from its own planet, Jupiter. But don't forget again that the planet Jupiter is 320 times bigger in terms of mass than the Earth is. So whatever effects the Earth has on the moon, this is going to be multiplied by a factor of 300 and something. So this is why, and in addition to that, you have the other basically two players. Europa is not this minor player, and it's not too far from it. And in addition to that, you have to a lesser extent Ganymede. Callisto is very far, 2 million kilometers is far away from this thing. So again, this is a tag of war, and that is why this object in here is really something that is big time in here. I think this is wrong. I don't think that this is correct. Okay, I think this applies. The ocean is for again, some of these studies they have to do with magnetism basically. So please correct your notes. Okay, they have to do with the how do we know we have oceans in here or not? Is because again the magnetic studies, because those probes, especially Galileo, when it went around the planets in here and the moons, it collected a lot of information about magnetism, and based on that, it deduced basically do we have a core, if it is, what type, and so on and so forth. And besides, it collects actually samples as they're kind of coming from here. This one is mainly sulfur. To put it in the words of Carl Sagan, basically, when he looked first pictures that started to come from IO, what did he say? This is desperately needs a shot of penicillin because of the fact that this is really super active. A lot of volcanoes, sulfuric volcanoes, basically. It's the most active in terms of volcanoes in here. So what does it get in there? Its energy again from the fact that it is basically needed all the time. This is 42.5 hours. It goes once. Goes super fast around its moon. This moon, around this planet, I'm sorry. This moon helped us in a lot of ways. First of all, when it was discovered, it was not discovered the same night. It was discovered the night after. As a matter of fact, if you go right now on the stellarium, for example, and you try to look at the moons of Jupiter as they look right now, okay? You zoom in on Jupiter and you will see the moons next to it. Of course, the closest one is going to be this one. But you will not see it probably now. If you move the hours a little bit on stellarium or before it, you will see actually coming. You will see it coming behind Jupiter. You will see it emerging because of this period, 42.5 hours, which is slightly more than a day and something. So if you wait, what is it, 24 hours? So if you wait a day and a half, slightly more than a day and a half, you will see that this one is going to come back again and go around Jupiter. It played a major role when Romer tried to determine, for example, the speed of light, because he used this moon and its revolution around Jupiter to estimate the velocity of light, because people believed, at least before him, that maybe light has a finite speed, but they didn't know how to measure it. Any measurement that Galileo did and people before him basically failed because of the fact that the light moved super fast. But if I look at the moon of Io, which is about 4 light years from us when we are at the closest distance, when we are on the other side where it's about 9 astronomical units, not light years, 9 astronomical versus 4 astronomical units, then we can account for the fact that, hey, what is it? Did I say 9? 5 plus 2. No, that's not 9. That's 7, okay? So basically 7 and, I'm sorry, let's do the math correctly. When we are at the closest, it's 4 4 AUs basically. And then you add to it 1 AU and 1 AU, so we're 6 AUs on the other side. Because we have 2 astronomical units when the Earth moves from one side to the other. Because we are 1 astronomical unit from the sun. So when we are on the other side, add to it 2. So basically, if we make this correction, how much extra time the light needed to reach us, and we know the distance is 2 astronomical units, he came up with an estimate of the velocity of light, how fast light travels to Earth, using this mode. So that's really astronomy still continue to play a major role in development of science in general, especially physics. And now even with this pandemic, people are talking about the viruses have some cosmic roots. So maybe there is some more to it than just this one. So it's an important subject in terms of its influence on science. So this one helped us, for example, measure the speed of light, at least the first measurement. After that, FISO came up with a better measurements using other apparatus. But the point is that this is a very close moon. It's super active. And as a matter of fact, these are some of the pictures of the volcanoes in here. These are the hundreds of kilometers. This dwarfs any kind of volcano that we have on Earth in here. These are super, super big volcanoes in here. They can extend basically to almost 1,000 kilometers above the surface. And this moon has lost most of its water basically a long time ago. And right now it's whatever rock basically that it's having. It's still losing a lot of its materials, and its detriment toward Jupiter, because of the fact that it's being always losing a lot of this material in that. Now, when Galileo came in up close trying to take pictures of this moon and study the moon itself, it was damaged actually because of the high energy particles that are emanating from the moon itself and being pulled toward the magnetic field of Jupiter. So that in itself was really a big problem, because some of the components, actually some of the electronics in Galileo, the probe itself, were damaged because of this flyby. So that's some of the things that we know about this ones in here. This is a big volcanoes. They are not small volcanoes. They're actually very large volcanoes. They extend very high, and actually the sulfur and the nitrogen and all of the components, when they escape very high speeds. And as they cool down, they rain back onto the surface, and that's basically how this moon looks like. So this is an interesting moon. It has some of the most violent activities in the solar system happens on this moon. And it's because of its proximity to its own host planet, namely Jupiter. Again, this is the picture taken over several months, basically from April, September until July of 1999 of the same region. And here, look at this spot in here that did not exist in here that it formed. Again, this is our volcanoes, and the colors, sometimes they use them to enhance the picture, but sometimes they're actually more realistic because of the fact that sulfur itself has this characteristics in it. Again, so this is the bottom line. The energy is coming from the fact that this is Jupiter on one side, Europa and Ganymede on the other, as far as IO is concerned. As far as Europa is concerned, it's actually Jupiter on one side, Jupiter and actually IO on one side, and Ganymede on the other side. Ganymede, as far as it's concerned, it has Europa on one side, and actually to a lesser extent also IO, and also big time Jupiter. Callisto is out of the picture; it's far away from them. So that's basically and in here you see some of the craters in here, and this is actually lava of sulfur in here that's forming on its surface. So this is basically the entire ground, the entire surface is really molten, as far as you can tell. This is a very, very active volcano. Again, in terms of the moons of Jupiter, this is the distance. The further away, this is ancient surface as far as Callisto. This is get closer to Ganymede. You have more now geology, and there is more activity on the surface. With the crater impacts, you can hardly see any kind of crater impacts whatsoever on Europa. It's mainly geological features on this planet. Of course, we're not showing in this picture IO. It's going to be more dramatic if we did. So the point being in here is distance matters. The further you are from Jupiter, the less basically the deader, if you wish, the object is, such as Callisto. So these are some of the moons, or at least the big moons of Jupiter that we need to know about in this case. Then, of course, we have the Titan and Triton. Those are two different moons from two different planets. And the two planets are Saturn for Titan, and Triton is for Neptune. So those are two different moons. Please do not confuse the two of them. Now, Titan is the one that is actually mentioned in the movie Interstellar, if you guys remember, if you have seen that movie, when actually at the end, the hero of the movie meets his daughter, She was actually living on Triton at that time. So Triton has a lot of basically potential actually for different form of life, if you wish, because of the fact that it has some unique properties. One of its properties that is unique to it, this is, by the way, that is the only object Triton is that we landed on, the only moon that we landed on outside of our moon. So that's the only object outside of this, in the entire solar system, as far as moons is concerned, other than the Earth's moon, that humans has sent a machine there to land on it. So we sent a lander actually, and the lander was called Huygens. Because actually Huygens in 1655 discovered it. And you see, we discovered the 4 moons of Galileo. Galileo discovered them, they're called the Galilean systems. And when Huygens looked at further away and he started analyzing the data, and he saw this something that is actually going around CHARON. And that's when Triton was discovered. And it's a big moon. It's one of the most amazing things if you had a chance to look at through a telescope. And unfortunately, we cannot go to campus, but we'll try to use our telescopes. If you look at the planet Saturn and you see its moons, it's really uplifting. You think that, hey, there is another world out there. The atmospheric pressure is slightly more than the actual atmospheric pressure on Earth. Right now, all of you right now, you're sitting in your own rooms. You're feeling on your shoulders, in your body, everywhere, about 100,000 pascals, which is 100,000 newtons per meter square. 100,000 newtons is about, what, 10,000 kilograms. 20,000 pounds, basically. You're lifting it on your shoulders. That's basically all of us, okay? Roughly, okay? So that's 20,000 pounds. I don't know how many 20,000 pounds. It's probably 20 tons, 20 US tons, that is. It's a big weight. Imagine that times and a half. Imagine if you are sitting right now on Triton, of course, barring the fact that we need oxygen or all of the other things, you will be supporting about 30,000 pounds, basically. It's not bad, honestly, compared to, for example, Venus. Remember, Venus is 90 times the atmospheric pressure. This is only 1.6 the atmospheric pressure. So this is good, okay? It's not as bad as sitting, for example, on Mars. Mars has very little, if anything, in terms of atmosphere. You're going to explode unless you are wearing proper protective gears to prevent you from exploding, so that they are pressurized also. You have to have pressure inside. So this one, potentially, other than feeling a little bit kind of a crunchy, a little bit, not that much, you should be able to sit fine on this moon. So that's one of the things that is nice about it, that the atmospheric pressure on it is not bad. However, it's not any atmosphere that we know. That's one problem. The other thing also, it's the temperature. This is a super cold moon compared to the Earth. As a matter of fact, it's cold enough so that the methane and ethane actually rain in terms of liquid. So what you look at when you are on the terrain of this moon, it looks like you are looking at lakes and oceans and shores and waves, actually. But it's not of water. It's actually of liquid, methane and ethane. That is really what it is. It's a really different kind of liquid, different kind of environment. And it rains, and actually the entire methane, and it goes through a cycle, just like, for example, the water cycle in here on the Earth, where you have water basically falls in, condenses, becomes liquid, then after that evaporates, comes as rain, and so on and so forth. You have a whole cycle basically for the water cycle. And on Triton, you have a similar cycle, except it's not for water. It's based on this gases. Again, the temperature here has a big say why that is the case. The temperature in here on the upper atmosphere is about, what, 180 Kelvin, at most 170 Kelvin. That is still too cold. Remember right now when we're sitting at 300 Kelvin. This is slightly half of what our temperature is. So it's way below freezing. So if there is any of us up there, we're going to freeze right away. So this is not comfortable environment in terms of temperature. And it dips even further the closer you get to the surface, in the teens of kelvins. So it's very, very cold in the atmosphere. That's why the methane and ethane become actually clouds. And then after that, it rises a little bit to just under 100 Kelvin. So the temperature is very, very cold on its surface. So cold, as a matter of fact, what you look at in here and you think that they are Rocky Mountains, they are not actually Rocky Mountains whatsoever. They're actually ice, water ice, okay? The temperature is so cold that the water itself is like the mountains and all of the things, the features in there. So if you are in there and you look at the rock, and actually we have some pictures that are actually sent by Huygens. Here are some of the pictures. These boulders in here, these particles in here, they're actually ice. They're not rock in a sense. If nobody told you that this one is what it is probably, and you might think that, hey, that's probably some sort of a desert here somewhere, with maybe some water in here that is on it. The reason why you can't say it's not a desert, because you don't see any plants in here. And this picture is taken as the Huygens was coming down. So there are several pictures in here from the very high to the bottom in here. The entire moon itself looks kind of hazy, orangey picture in here. And that is because of the fact that the radiation from the sun that it received, albeit very little, it's actually diffused throughout its surface by this clouds of ethane and methane that it has in its surface. And that apparently has all kinds of effects on the moon itself. As a matter of fact, the surface itself shows very hardly any kind of cratering whatsoever, because the geology there is very rich, just like as much as geology is on Earth in here because of the wind and the water and all of those cycles. That's a similar one in there, except that the cycle in there is not driven by water as we know it in here on Earth. It's driven by different kind of liquid and other forms of liquid that basically drive this mechanism in there. And look at these rocks in here. They look like, or at least what looks like rocks, actually, like I said, they're actually being weathered by the same liquid, by the same phenomenon as rocks are weathered in here on Earth. But again, weathered by the liquid methane and ethane in there that forms those lakes and those shores of waves that hit in there. So this is an interesting word, actually. And the chemistry there is kind of complicated a little bit because it involves a lot of basically bio-based, carbon-based, basically biology in there. What looks like it's carbon-based chemistry, I should say, biochemistry to be more specific. That hey, maybe if there is any kind of life form, because it needs to extract energy not from from whatever source that it has in there, but does not use oxygen as a mechanism of oxidation or anything like that. For one thing, and what's a big reason, is the fact that this is a very low temperature phenomenon. This does not happen at room temperature, for example, required for our oxygen and all of these things to happen in our planet. So it's still an enticing word that people are really interested in trying to go to, trying to understand more. And if in case we discover a different form of life, until now we're not successful, that is non-carbon based room temperature life on Earth, like for example, the one we have on Earth. But it uses more like nitrogen, more like methane as forms of energy exchange mechanism, and probably will not survive and outside of that environment, and will require that, and would think that probably that is how life should be. Then hey, that opens up the whole different kind of ball game for as far as looking for exoplanets and see what kind of life they can support and what kind of things that they can have. So there is a lot of things that this moon has taught us, and it was in it was actually very good that we had a lander on it from Galileo's mission. Galileo is the one that sent Huygens. Huygens actually had a parachute and landed on the moon and stayed there for about more than an hour and a half, collecting data, relaying it through Galileo, and Galileo was sending it to NASA. And basically the pictures there and the stuff that we received from the moon are outstanding. Okay. Another moon, as I said in here, that was actually part of a flyby is actually Triton. Triton is the moon of is the big moon of Neptune, and it's not as big as the other moons actually, but it's big. It has a very big coefficient of reflection in here. If you look at this table again, if you go back to it, Okay, we didn't have it. We didn't include it. I'm sorry. It has a big coefficient of reflection, which means something very important in here when it comes to moons, okay? When it comes to planets in general. That means it doesn't retain the heat for it to heat up and return it back in a different form of radiation, like infrared, for example. Like what's happening, for example, big time on Venus, and what happens a lot also on Earth. It receives a lot of radiation, absorbs it, then reflects it back. So basically, there is a high absorption coefficient in here for this object. Relatively speaking, compared to Triton. Triton reflects most of the radiation, so basically at the end it doesn't get into much heat. So its temperature actually is very, very low. On average, between 30 to 40 Kelvin. That is very, very low. By the way, you cannot have a negative temperature in Kelvin. Kelvin is an absolute temperature, the lowest temperature you can have, and you cannot do that. It's impossible to reach a 0 Kelvin. Is 0 Kelvin. So you cannot do 0 Kelvin. That's a theoretical limit that you cannot do in lab. In practice. The universe right now is few degrees Kelvin on average, and this moon is very, very cold to the point that actually the nitrogen now is the one that is going to erupt, not even water in this case. So nitrogen is actually frozen, and then when it heats up a little bit and the temperature rises, it emerges as volcanoes. So this is actually a very cold universe, very cold basically world. And that is Triton. It's the moon of it has St. Peter's not too far actually from then in terms of the, yeah, it's in here actually, you can see it too, in terms of the cracks in its surface too, okay? And it has volcanoes, as I said before, okay? So right now it's 3 o'clock, and I have a quick tool in here, because I don't want to forget this. Okay. We are slightly more than halfway. Let me tell you what is coming next, so that we have. We are going to talk about Pluto and its moon CHARON. That is the next thing that we need to explore, and we're going to talk about also the rings. Okay, and then that is the entire chapter in here. So right now it's 3 o'clock. I know we still have about 15-20 minutes basically left, but because we're going to probably disrupt the whole topic midway, and I really hate to do that. And I want to come next Thursday and finish basically the lecture, the notes you guys have. I'm gonna put the assignment today, actually. Worst case scenario, tomorrow I'll finish the assignment for you guys, and it's gonna be due next week. All of the assignments are gonna be due next week. So hopefully you will start on them, and hopefully you will have a look at them before Thursday, so that if you have any questions, you are going to ask them. Now, Tuesday of next week, Tuesday and Thursday of next week, there will be no live sessions. But I will be available for you guys should you have any questions. Basically, if you're having difficulty with your project, or if you have with your assignments or something like that, I will be in session in here available for you guys. However, I will be only between 2 and 2:30 by myself, meaning if somebody comes in and says, you know what, I have a question, or sends me an email saying that I want to be there, I will be here forever. I will be here until the period is over, so that we're clear on that. Now, if nobody shows up by 2 o'clock, if nobody sends me a notification, by 2:30, I'm going to leave the session basically and not stay in here unless one of you guys sends a request. I try, and I think I have been to a lot of extent successful in responding right away to your requests and going on live with you guys and do whatever you guys want to do. So I want to keep that, whether we're meeting on Tuesday next week or not, whether we're meeting on Thursday next week or not. But the point being in here, I will be here next week because we're done with we'll be done with the materials as far as next week is concerned. So there will be no live sessions next week, no synchronous basically sessions like we're doing this week. And hopefully you guys will have will be basically done with what you need to do in terms of your assignments, in terms of the quizzes, And the last exam is going to be scheduled on, because that's how the campus schedules them. I don't want to schedule outside of how the campus schedules because you might have other classes, and I don't want to give you an assignment on the same day when you need to be doing another exam. So that's for the final exam, okay? Does this sound like it's a good plan, or should I make changes to it? Okay, good. So everybody at least who responded agrees. Who did not respond, I assume that they did. Okay, Carissa, what happened? Carissa, do you have feedback, please? Oh, okay. Because it came out as no, I didn't understand. Okay, very good. So even Carissa agrees with that. Okay, very good. So Thursday, we're going to meet again at 2 o'clock. We're going to finish this chapter. We're going to talk a little bit of the story of how basically Pluto was discovered, which is a big story in itself. Okay, it's different than all of the other objects that were discovered, and how people were confused about Pluto initially, thinking that it must be bigger than the Earth, and then later on realized no, it's not. And then how actually the moon of Pluto was discovered, which is an interesting story in itself. Also, how the idea evolved and how basically looking at the different pictures and say, you know what, this seems to, luminosity of this planet seems to be changing. The only way that could be is because there is probably an object next to it that increases and decreases the luminosity. So that's when CHARON was discovered, and how the person who discovered it actually struggled with naming it because he wanted to name it after his wife, and at the end succeeded in doing both, satisfying the requirement for naming it after his wife, and at the same time naming it after the one of the mythology, basically goddess in that. So basically gods in that. So that's basically how an interesting story in that. And then we will talk, and very, very important, about the rings, okay, which is a big deal, okay? So we really have to have an understanding of how rings form, where they form, and how they are basically formed. And barring anything else, I may even have to do a simulation to see if we can make rings for the Earth. Because at some point, we will see that this feature is not really something that is unique to the big planets too. At some point, probably most of the objects had rings, and later on they settled somehow somewhere else, okay? Okay, I see you guys Thursday, and please stay safe unless you guys have any question. Nope. Okay. Good luck and bye.